Hello and welcome to this series of videos where we are looking at the setup and the running of the NC4 Plus Blue. Today we're going to be looking at the broken tool detection. Again, we have Ian with us here today, who has all the knowledge and the know-how on the NC4 Plus. So Ian, first question, what is broken tool detection?
Well, after the tool has been used for machining, we are checking the tool against the value in the tool offset. If it's shorter, that typically means the tool is broken. If it's longer, that means the tool is pulled out during machining.
Okay, so are we actually measuring a tool here?
No, the cycle assumes the tool has already been measured, and using that offset value and a tolerance, we will position the tool in the beam, check the tool for being broken, and then we'll tract out of the beam, check the tool for being long, okay, before returning to the home position.
So Ian, you mentioned tolerance there. Is there some default value, or is this something the user can change themselves?
Yes, the tolerance is a cycle input, but if no input is entered, then the cycle assumes 0.5 millimeters as the default value.
Basically, the tool will go into the beam by 0.5 millimeter, carry out a broken tool check, and then go above the beam by 0.5 millimeter and carry out a pull-out check.
Yes, that's correct.
Okay, so what would happen if the user or operator didn't use a broken tool check?
Well, the danger is you're potentially putting a tool back into the tool carousel that is not fit to cut. Next time it's used, it could damage or scrap the part, or if it's pulled out excessively, it could even cause a collision.
So when would the user typically run a broken tool check? Would it be something they do at the start or mid-cycle, or something they do at the end of the cycle?
It depends on the nature of the job. If you're machining a component with many small holes, you might want to do a broken tool check between drilling each hole. But the majority of customers always check their tool after machining, just before they put their tool back into the carousel.
What about checking for chips along the flutes?
The cycles we're running today don't check for chips further up the flutes. Since those cycles are more involved, we'll be doing those in a later video. Today, we're just doing simple broken tool detection.
We have two broken tool detection cycles. We have the 9863 cycle and we have the 9866 cycle. So Ian, why do we have two cycles?
So 9863 is our standard broken tool cycle, and that's available with all Renishaw laser systems. 9866 is a high-speed broken tool cycle, which uses a special mode that must be enabled by the installer. Therefore, it's not always available.
Ian, how do people know if the 9866 cycle is available?
So you take a tool, a drill that you know is good, and you run the 9866 cycle. If it passes with no alarms, then you know the cycle is actually enabled and the mode is working. If you get an alarm, then you know the mode is not enabled.
So apart from 9866 being high speed, what other differences are there?
The 9863 cycle can check all tool types. The 9866 cycle is designed for drills, taps and reamers. As already mentioned, it's very fast, but it's extremely reliable in very wet conditions.
Okay, so we're going to start off with the 9863 standard cycle, and then we'll move on to the high-speed 9866 cycle afterwards. So we set up the machine with three tools. We have tool 1, which we've measured, and we know is okay, we haven't tampered with. Tool 2, we pre-measured, but we accidentally, or someone accidentally broke it. And then tool 3, we have a tap, again we pre-measured, but during operation it pulled out. So Ian, let's get on with it, let's do some checking. Can we check tool 1, which we know is okay?
Right, so here is my NC program, and the first thing you'll notice is I've made the tool offset active before the cycle. This is very important. The second thing is this tool has been pre-measured, so we know the value in the tool offset is correct. So I'm going to enter the cycle input now, and I'm going to use the GoPro back because it makes life easy. So first of all, it asks me what is the tool number for the tool we're going to check. In this example, it's 9, so I'll enter 9. It's asking me what tolerance I want to use, how far do I want to put the tool into the beam for the check, and I want to use 0.2 millimeters. It's now asking me for a spindle speed to use during the checking. The default value is 3000, and I'm quite happy with that. And it's asking me for any Y step over. Well, today we're going to check the tool on center. So I'm ready to type in now. So I type in G65 P9863. I put in the tolerance value, which is H.2, okay, and the tool number, which is T9. And we're now ready to press cycle start.
Okay, so no alarms were issued there, which means the tool passed its broken tool check, as we thought it would do. So Ian, can we move on to tool 2 now, which we know is broken?
Yes, certainly. I've changed the tool number and applied the tool offset as before.
Okay, so a broken tool alarm has been issued, as we expected. So can we move on to tool 3 now, which is the tap, which was poured out during operation. Are there any changes needed to the input line for this?
Yes, if we want to check for tool pull-out, we need to modify the H input, making it negative. So both long and short conditions are checked, using a tolerance of 0.2.
Okay then, so just to clarify, we can either check the broken tool on its own, or we can do broken tool and pull out. We can't do pull out on its own, can we?
That's correct.
Okay, so we've seen both alarms being issued, one for broken tool and one for pull out. This will tell the operator that something is wrong. The machine would just stop. But what about if you want to run unmanned and you don't want to stop production?
Well, if you add M1 to the cycle input line, the alarm will be suppressed and we'll set variable #148. If after the cycle is run #148 is a 0, that means the tool was good. If it's set to a 1, it means the tool was broken. If it is set to a 2, it means the tool was pulled out. Therefore, a programmer can build logic around the status of #148, maybe called a sister tool or something similar, and there are examples in our programming guide of how to do this.
Okay, so we've seen 9863 in action. Can we move on to the high-speed 966 cycle and do a check on the tap for the people watching?
Yeah, sure. So I just need to change the cycle input line from 9863 to 9866. All the other inputs are exactly the same.
Okay, so this looked very similar to 9863 in terms of speed, but we are running dry. I guess this would be more noticeable in wet conditions?
Yes, 9866 really comes into its own when the coolant levels are very high.
We've used our NC4 Plus Blue today, but some people might be more familiar with our TRS2 for broken tool detection. What are the differences between the two systems?
Well, you can detect broken tools with TRS2 or NC4. There are some advantages with NC4. You can detect a wider range of tools. It's more reliable in extremely wet conditions. With NC4, you can also measure tools and undertake more complex tasks. It's really the Swiss Army knife of tool setters.
When would someone use the TRS2?
Detecting broken tools with TRS2 has some advantages. The unit is small and compact and can be mounted outside the working area with the laser beam pointing near the workpiece. This means when you're checking the tool, all movement is minimized and therefore reducing cycle time.
Okay, so just to sum it up, the TRS2 is just used for broken tool detection, whereas the NC4 is a better choice if you want to do measurement or any advanced functions.
Yes, that's correct.
Thank you, Ian. So today we have covered broken tool detection. I hope this has been of some use to you. See you on the next video, and remember, check your tools.